Hi friends, today we are going to introduce a new topic which we call as analysis of finite word length effect. Now before going into any further in this topic, we need to first understand why we need to study this topic. Okay, so in DSP, what is the major role of this topic? This topic is actually restricts the practical application or implementation of a given theory in DSP. In DSP, up till now, whatever we have done, assuming all idealized conditions. Today onwards, we are going to understand what will be the effect or what will be the practical implementation or practical limitation of implementing a DSP with some finite resistor length. So before going into the actual topic, we will first understand how and what is the representation of numbers in a DSP. So we are going to see today what is a number representation. Now in a number representation, okay, what we are going to do in DSP is we are gonna build some special kind of a hardware sometimes, or sometimes we will use computers. We often use computers also. For example, if I have a signal coming from a seismographic event, like there is some earthquake, the sensors has picked up some data, the data has been traced in some electronical way, and the data has been stored in the computer. Now to extract the particular information from this signal, we will use DSPs, or we will use the DSP techniques, that is digital signal processing. For example, in this seismographic signals, there could be much of the noise present. So I need to actually have a filtering effect. The amplitude might go very haywide. So I need to actually restrict the amplitudes. With all these operations can be done using a DSP, because the speed required, okay, to analyze this type of events is very high. So what we will do is we will implement a DSP algorithm or run a DSP algorithm on a particular computer either using a special hardware or using the existing hardware of the computer. And then this algorithm will actually help us in filtering, noise removal and various applications on the given signal. So with respect to computers and a special hardware, we will restrict ourselves in usage of binary data. We know that computer always speaks in the language of binary data. So in number representation, I will be using binary representation of my data. So whatever will be the data that is coming from to me in any form would be converted to binary representation. Binary representation, that means the base or the radix is 2. Okay, what are the example of this number? I'll take a number. For example, we have 13 to the base 10. Now this is called as the base or radix. Now 13 is a number with radix 10. Okay, 10 stands for decimal number system. So this number that I have 13 is in which number system? It is in decimal number system. I am going to represent this number 13 into binary. Now what do you mean by binary? It will have a radix of 2. With radix of 2, the maximum numbers that I can have is 0 and 1. So I can speak only in 2 number language, that is either I'll put a 0 or I'll put a 1. So I have freedom of putting only zeros and ones. Okay. Now how 13 will be represented in zeros and ones? We will use 4-bit values. So it will be 1, 0, 1, 1. How I got this number? This is my units place, which we called as 2 raised to 0. The base is 2. So 2 raised to 0. This is 2 raised to 1. This is 2 raised to 2 and this is 2 raised to 3. Okay, 2 raised to 3 is 8. So 1 into 8. Next, 2 raised to 2. So it will be 1 into 4. Next, 2 raised to 1. It will be 0 into 2 raised to 1. And finally, 2 raised to 0, which is 1 into 2 raised to 0. Correct? So what it will give me? See, 1 into 8, 8 plus 1 into 4, 4. So 8 plus 4, 12. 0 into any number is 0. And then 1 into 2 raised to 0 is also 1. So 1 is added with 12. So that will give me 30. Okay. So this is which place? Units place, I can say. This is which place? 2's place. This is 4's place. This is 8's place. And so on and so forth. It will be 16's place and then 32's place and 64's place. So this will, the increasing order will increase in terms of 2. Similar way, in decimal number system, we have units place. Okay. For example, in decimal number system, I write 13 to be 10 raised to 0, which is the units place. Then we have 10 raised to 1, which is nothing but 10's place. When we add them both, you have this 1 into 10 plus 3 into 1. Okay, so this will give me 3, this will give me 10, and when you add, you will get 13. So when the index or the base is 10, you will have 10 raised to 0, 10 raised to 1, 10 raised to 2, and this will be the positions of the number. When you have base as 2, okay, then my base will be 2 raised to 0, 2 raised to 1, 2 raised to 2. And the numbers that I can put in any place is either 0 or 1. Okay, in binary number system, I can put either 0 or 1, that is 2. If you start from 0 and then next number is 1, that is 2 numbers. For decimal number system, whereas we can put the numbers from 0 to 9, that are total 10 numbers, right? So 1 and 3 is in between 0 to 9. So all the numbers will be in 0 to 9, and the place of the number decides its importance, whether it is in the units place or whether it is in the tens place or whether it is in the hundreds place, and so on and so forth. Okay, so this is how we convert the decimal numbers into binary numbers. And now so on and so forth, we will only use the binary representation. Okay, in binary representation, okay, now we have used 4 total digits, and each digit in a binary number system is called as a bit. So we have this called as this is a 1 bit. This is also second bit. Okay, third bit and 4 bits. So 13 in decimal can be represented using 4 bits in binary representation. So we write this as 13 to the base 10 will be 1101 to the base 2. This base 2 indicates that it's a binary representation. And how many total bits? Total there are 4 bits. Okay, so each number or each digit is now called it as a bit. So these are all bits. Total number of bits is called as the word length, or we called it as word. Okay, so what is the word length of this number? It is 4 bit in length. Okay, so we have understood that in the chapter name, I said that it is analysis of finite word length effect, right? So the name word length come from the number of bits used to represent the data. Okay, so I'll be now onwards we'll be using all binary representation. So we will be dealing with binary numbers which can take either 0 or 1 values, and there will be series of these digits, and the total pack of digits we called it as a word. Okay, so this is what a number representation in DSP is all about. Now let us take one more number. This number is very simple, so let us take one more number. I take a number 9.375. 5. Okay, so how to represent a number 9.30375 into its binary equivalent? So we will be using, okay, let's say I wanted to show it in binary. Okay, now what I'll do is I'll represent this. This is my integer part, and this we called as a fractional part, right? So now in a given decimal number, I have two forms or two separation. One is called as a integral part or integer part, and one is called as a fractional part. And the dot that you see in between this one is called as a decimal point. So decimal point is a separation between integer and fractions. Okay. Now the integer part will take the order to the base 10 as positive. Like this will be 10 raised to 0, then 10 raised to 1, 10 raised to 2, and so on and so forth. Which side? It will be on this side. So integer, when I am writing an integer, the least order, okay, the least order of the index in will be on the extreme left, okay, of the decimal point, and from there onwards it will start increasing. So when I move this side, the order of the index of 10 will start increasing. Here it will be 10 raised to 0. Remember, it will start from 0 and maximum will be 1 minus. Like for example, I wanted to write, if I write 1000, then it will be 10 raised to 0, 10 raised to 1, 10 raised to 2, and 10 raised to 3, right? Even though there are 4 digits, I'm not going up to 10 raised to 4, I'm going 10 raised to 3. Okay, why? Because I'm starting with 0. Okay, so 1 bit less or 1 index less. But in the same way, when I'm moving from in the fractional part, that is from the point towards in the fractional part side, the minimum value of the index will be just immediately right to the point, and then onwards it will start increasing. But here the increase will be in the negative index. For example, this 3 is 10 raised to minus 1 position. 7 is at 10 raised to minus 2 position. And 5 is at 10 raised to minus 3 position. And we know that 10 raised to minus 1 is 1 upon 10. Minus 2 is 1 upon 100. And 10 raised to minus 3 is 1 upon 1000. Who is the least? 1 upon 1000 is the least. So immediately next to the decimal point is the highest index. And as I go on increasing or moving away from the point towards right, the index will start decreasing. Agreed? So this is how a decimal or a fractional number is represented in a decimal number system. Same way we will be designing or defining a number in a binary way. Okay. For example, we will have an integer binary and we will have a fractional binary. Correct? As what we had in the decimal number. Integer is 9 over here. So I will write integer to be 9 to the base 10, which will be represented using ones and zeros, and that will give me the value as 1001. So that's not a problem. To the base 2. So I got the integer part, so I'll write the integer part 1001. Now the fractional part that is left with me is 0.375 to the base 10. Now what will be its conversion to get the number as 0.375? Now here also we will apply the same logic. After point, I will start having index in the negative way. Okay. Now, for example, let us take this fractional part, that is 0.375, and let us do the representation. So I have 0.375 in the 10's value or to the base 10. Now I want a binary number. So any binary number, okay, I'll mark a point over here. Here it will be 2 raised to 0, here it will be 2 raised to 1, 2 raised to 2, and so on and so forth, okay, in the positive way. And on the right side, it will be 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, and so on and so forth. So here the index will be decreasing. And here this side the index will be increasing. What do you mean by index? Index means I'm saying that minus 1 is greater than minus 3. Okay, and what this point is called as? This point in the decimal number system is called as a decimal point. Binary representation, this point called it as a binary point, analogous to that of the decimal point. Okay, so the point that I denote over here in the number is called as a binary point. Fine. Now what we will do is, I want 0.375. Okay, so there is no question of putting anything because here it is 0. So I'll have 0 point, correct? What is 2 raised to minus 1? 2 raised to minus 1 is 1 upon 2 plus 2 raised to minus 2 is 1 upon 4 plus 2 raised to minus 3 will be 1 upon 8 and so on and so forth it will go. Correct. Now, okay, I can take 1 over here, okay, but if I put 1 under 1 by 2, it will be 0.5. Required is 0.3. It will be very much greater than 0.5. So I don't need 1 by 2. So I'll put a 0 below it because I'm going to do multiplication over here, right? Then 1 by 4 is 0.25. Agreed. It's okay. 0.25. So I'll put 1 over here multiplied. So now I got 0.25. So I got 0.25. Now whatever is remaining that I need to add. Okay. 0.25 I want 3 in the place. So below 2 I want 1. And there is 0.25. So I want so 1 by 4 I can write it like this. Too much of verbal things will ruin up. So I have 0.25. Okay. If I add 0.125 to it, then I'm going to get 5 as it is. 5 to 7, 1, 2, 3, and it is 0.375. 0.125 is 1 by 8. So I'll multiply by 1. And I don't need to go any other further. So I'll put next as 0. No problem, you can have only 3 digits also. That depends on what level of digits you are using. Whether you are using 3 digits or 4 digits or 6 digits. If I would be using 6 digits, I will put all zeros after this number. Okay, so 0.375 in the decimal, okay, will be 0.375 in the decimal will be represented as 0 point because there is nothing ahead. So 0 point. And here it is 0, 1, 1, 0. So it will be 0, 1, 1, 0 to the base 2. Correct? But my number is not 0.375. My number is 9.375. So the total number, that is 9.375 to the base 10, will be having an integer part which is 1001, which is for 9, and then 0, 1, 1, 0 to the base 2. This is my binary point, and this is my decimal point. Understood? So how a fraction has been represented or a rational number is been represented using binary representation. We will have separate integral part, binary representation, and fractional part, binary representation, and with the dot we normally separate them. The dot is called as a binary point. In textbook, they normally don't put points. They normally use a very different symbol, and that symbol is of like this. So they normally show with a small triangle or small delta to represent the binary point, just to differentiate the binary point from the decimal point. That's the only reason. But it is not mandatory that you also use a triangle. You can also use a point over there. So this is how a number, a fractional and an integer number is represented in DSP. Okay, and we will be using binary representation. I hope you have understood that why we need a binary representation in DSP's application. Thank you.